Okay, so let's get started, please. Okay. So we're talking more about, we basically just introduced the notion of continuity. And we have these two definitions, right? That f is continuous at some point x naught. But we had what we're using as the definition, right? If for all epsilon greater than 0, there exists a delta, such that if the distance from x to x naught is less than delta, then the distance of f of x from f of x naught is less than epsilon. That's what we're taking as the definition. We saw that there was an equivalent formulation, right, that f is continuous at x naught if it turns out to be equivalent to saying that given any sequence xn that converges to x naught, the sequence f of xn converges to f of x naught. Right? So we saw that the definition was equivalent to this characterization. Right? Okay. So you don't really need to copy this, right? You should have it in your notes already a couple times. Okay. One way of thinking about it, is like this. What we're saying is that that the limit of for any xn converging to x naught, the limit of f of xn as n goes to infinity should be f of x naught, right? But let me rewrite this a little bit. This is, you can say that the limit of f of xn is f of the limit of xn as n goes to infinity. Right? The limit of f of xn as n goes to infinity is f of the limit of xn as n goes to infinity. Right? Because this is x naught. Right? xn converges to x naught. So this is just another way of writing your x naught. Okay? So what's continuity? Continuity is basically saying that you can pass the limit through the function. You can pass the limit through the function. You can commute the limit and the function. The limit of the function is the function of the limit. Okay? You can switch the order. You can switch the order without affecting the result. Okay? So that's exactly the same thing. All we're doing is saying what we said down here, but just to point out that it could be viewed in this way of commuting things. Okay.
And then this is true for all continuous functions?
Yeah. So what this means, right? What this means is continuity at that point x naught. Okay.
But when we say that this is a property of the functions, that you can take limit inside and outside the bracket.
If it's continuous.
If it's continuous.
Yeah.
Okay,
It's not true in general.
Got it.
Yeah. Okay. So.
Is it an if and only if situation? So like if we get to a point where we say the limits can commute inside and out, then we could say, okay, then we know it's continuous. And also if we know it's continuous, then we can do that property.
Well, it's a little bit, you have to be a little bit careful about how you word it, because this thing, because we introduced limits being equal to infinity, so you don't want to talk about a sequence that goes to infinity, because then you'd be talking about your function being continuous at infinity, which doesn't really make any sense for us. Okay.
Okay.
But for a finite, if this is converging to a finite point, okay, if this is converging to a finite point C, okay, then this is equivalent to f being continuous at C.
Okay. And it's an if and only if
Yes,
situation.
equivalent to. Yeah. So if and only if.
Okay.
Okay. Okay. So now we're going to do some properties of continuous functions. Okay. First one, continuity and arithmetic. Okay. Continuity and arithmetic, which you can guess is going to be a consequence of limits and arithmetic. So you can probably guess the form of it. If f and g are continuous at some point x naught, then f plus g, f times g, and f divided by g are all continuous at x naught. The last, if g of x naught is not zero. Only if g of x naught is not zero. Okay, and the proof is just use limits and arithmetic, right? Right? If I'm saying, right, if xn goes to x naught, does f plus g xn go to f plus g of x naught? Right. Right? So you just use limits and arithmetic, right? You say, well, look, the limit of f of xn plus g of xn, as n goes to infinity, is the limit of f of xn plus the limit of g of xn, right? By limits and arithmetic, and that's going to be by continuity. That's f of x naught. This is g of x naught. Okay, so it's easy. The limit of this is f of x naught, because f is continuous, right? F is continuous at x naught, g is continuous at x naught, right? And so you get f plus g of x naught. Okay. And then the other two are proved, identically. Any questions? Some people look a little confused.
What is this notion when we take a function of a name plus another function of a name? Or like f plus g, what does that mean?
What does f plus g mean?
Yeah.
It's the function, so f plus g is just a function defined as f of x plus g of x.
Okay.
Right. F over g of x is just a function f of x over g of x. Right? F times g of x is f of x times g of x. So that's just a notation. Yeah, Yannick.
At the first line, when you say, well, limit of f of x plus, do you mean to parentheses around the f of x plus g of x, or are you just saying the limit of f of x?
Well, you could have a parenthesis. Maybe it's more proper to do that, but it's pretty clear because you've got an n here, right? So this is g of x of n. So it's got to be part of this.
Oh, really?
Right? Yeah, because this n is here, right? What does g of x of n mean? If that g of x of n were outside, what is this n? N is the index going to infinity,
Yeah.
right? It has no meaning at all then, right? So it's sort of like, by context, you know it's got to be it's got to be in the parentheses,
Interesting.
Right.
Okay.
right? Because n has to have a meaning, right? Yeah.
Don't we have a situation, like the line above does f plus g times xn. We use xn there and we don't have a problem.
Yeah, because it's understood that with this arrow, that n is your index, right? That n is, right? What does this mean? You're taking the limit, right, as n goes to infinity. So n is your index, right?
Okay.
Yeah. Okay. Okay. Let me just show you how this would be done, the epsilon delta argument. Okay. So how to prove that f plus g is continuous at x naught via the epsilon delta argument. Okay. Okay. So, right, so you're given that f and g are continuous at x naught. You want to show that f plus g is continuous at x naught. Okay. Well, what does that mean? That means that given any epsilon, still, I know, given any epsilon, there exists a delta such that if the distance of x to x naught is less than delta, then the distance of f plus g of x to f plus g of x naught is less than epsilon. Right? That's the definition, right? We want to show that this function is continuous at x naught. That means, given any epsilon, we can make f plus g of x with an epsilon of f plus g of x naught, as long as we're given control over how close to x naught we are. Okay? So you say, okay, well, we know that these guys are continuous at x naught, right? So by hypothesis, we know there exists a delta 1 and a delta 2 such that if the distance of x to x naught is less than delta 1, then the distance of f of x to f of x naught is smaller than epsilon over 2. And if the distance of x to x naught is less than delta 2, then the distance of g of x to g of x naught is also less than epsilon over 2. Right? Okay. And so we have our two functions, right? We have our two functions, and they're both continuous here. We have some sort of sum function. Right? We have some sort of sum function, and we want to show that that guy is continuous at the same point, right? And so we say, well, look, I have one delta that makes everybody within epsilon over 2, makes these guys within epsilon over 2 here. I have another delta that makes these guys within epsilon over 2 here. Well then, within the common region, these guys are within epsilon over 2, and these guys are within epsilon over 2, and so the sum is going to be within epsilon of that thing. We say, okay, so let's write it out, right? So then, if we let delta be the minimum of delta 1 and delta 2, we see that x minus x naught being less than delta implies both of these things, right? That both of these things are going to be true. Right, let's call this one implies 1 and 2. So the distance of f plus g of x minus f minus f plus g of x naught. What am I going to do now? I'm going to use triangle inequality, right? So you say this is less than or equal to f of x minus f of x naught plus g of x minus g of x naught, right? Which is less than epsilon over 2 plus epsilon over 2, which is epsilon. Okay, so
do we just distribute? Separate terms? Distribute the f.
well, I mean, this thing here, remember, is f of x plus g of x.
Okay.
This thing here is f of x naught plus g of x naught.
Okay.
Right? So it's not distributing. It's rather just taking different, rearranging here. Okay. Which you may recall is basically what we did in the limits and arithmetic theorem, right? To prove that the limit of a sum is the sum of the limits, right? This is exactly the same argument. Okay, so you either do it earlier and set up your machinery and then use your machinery, or you don't set up your machinery and then do everything by hand. Okay, and basically the other proofs will basically be following the proof of limits and arithmetic. Okay, so let's go on. So the next thing is something that Nick asked a couple of classes ago about continuity and compositions. So here it is. If f is continuous at x naught and g continuous at f of x naught, then g composed with f is continuous at x naught. So you have a composition of functions, right? You've got a point x naught and a function f that's continuous there. You have a point, you have the image of that, f of x naught, and you have the function continuous there. And you want to know, you want to say that this composite function is continuous from here to here. Okay, so remember the goal, right? I'm going to do this the epsilon delta way. So the goal of the epsilon delta game is if somebody gives you an epsilon, can you find a delta neighborhood? Can you find a delta neighborhood that the composed function maps into this epsilon neighborhood? Right? That's the goal. Okay. And the tools you have, the pieces that you have to achieve that goal are that these guys are continuous from here to here and from here to here, right? So you know that if I'm given an epsilon neighborhood here, there is a eta neighborhood here that G maps into here, right? And I know that if I'm given some neighborhood here, there is a delta neighborhood that F maps inside of here, right? So if F maps that delta neighborhood inside of here and G maps the eta neighborhood inside of here, well then the composite function will map the delta neighborhood into here. Okay, so that's the strategy, right? You just use the continuity of these intermediate pieces to get the continuity of the composition. Okay, so let's write it up. Let's write it up. It's pretty straightforward. Given epsilon greater than 0, we know since G is continuous at f of x naught, that there exists a delta, I'm sorry, let me call it eta, there exists an eta greater than 0, such that if the distance of y to f of x naught is smaller than eta, then the distance of g of y to g of f of x naught is smaller than epsilon. Right, so I'm going to use y as my variable in this middle world. Okay, so we know that as long as the y's are close to f of x naught, then g of y is going to be close to g of f of x naught. Okay, so now we feed that eta into the definition of continuity for f. Okay, and so we say, well, look, since f is continuous at x naught, we know there exists a delta such that if the distance of x to x naught is less than delta, then the distance of f of x to f of x naught is less than eta. But then, the distance of x from x naught is less than delta, we see that f of x minus f of x naught is less than eta. And then g of f of x minus g of f of x naught is less than epsilon.
So I'm a little confused why, when we're starting off, we're using, never mind.
Okay, good. You got it. Good. Yeah, Adrian.
Oh, why can't we just have y for the middle one, or does it matter because that isn't part of the epsilon delta?
Well, what we're saying is that any point y that's within eta of f of x naught will have an image that's within epsilon of g of f of x naught. Okay? So, any y will do that. Well, f of x is within eta of f of x naught. So we can use it. We can use this property, right? Anybody who's within eta will be, their outputs will be within epsilon of g of f of x naught. So as long as we have somebody within eta, for example, f of x, then its output will be within epsilon, right? And so we found, right? So, we've created a satisfactory delta. Right. We've shown that we can play the epsilon delta game successfully. Okay. Everybody all right? Everybody all right? Except for Hogan, who's sleepy.
Sorry, I'm so sorry.
It's okay. It's okay. Sorry. Okay. Any questions? Any questions? This is pretty straightforward. Okay, right? Okay. Yeah. Okay. Now let's go on to section 18. Section 18, theorems about continuous functions. I mean, we've already been giving theorems about continuous functions, but these are, like, maybe I should call it important theorems. These are like pretty cool theorems. In my notes I have or the triumph of Bolzano-Weierstrass. Because we're going to use Bolzano-Weierstrass like there's no tomorrow. Okay.
Because if there was no tomorrow, it would be in Bolzano-Weierstrass.
Okay. So I've got some good lines in my notes, and let me just use them. Today we will finally explain some of the mysterious claims made in calculus classes. So here's the first theorem, and this is not maybe the most important one by far. But it says this: if you have a continuous function on a closed and bounded interval, then the function is bounded. That is, the image of the function lies between two values. Okay, so right, you have some closed interval, a, b. Right, you have some function. You know that there's going to be some. Make it negative so that it's more understood. You know that there's going to be. You're guaranteed some sort of upper bound, and you're guaranteed some sort of lower bound to it. Okay, not true if the function is open. I'm sorry, if the interval is open, right? If you're on 0, Aria.
Oh, please finish your...
If you're on 0, 1, say, and have the continuous function 1 over x, right? It's not bounded, right? It goes up towards infinity, right? But if if your interval is bounded, I'm sorry, if your interval is closed, right? That's kind of a funny thing, right? It doesn't, it's false. The boundedness doesn't do it for you. The boundedness of the interval doesn't suffice. You need it to be bounded and closed. Okay. In that case, the function is bounded. Yeah, Aria.
Well, my question was just, we're saying f is bounded, but wouldn't it be more correct to say f is bounded for that interval? Because you can have a function that is continuous on an interval, but is still not bounded, like in general.
But if we don't even know the function is defined outside of this interval at this point, so we don't. If we have a function, we say let's say we have a function on AB, we don't consider it outside of that AB.
Okay.
So yeah, I mean you could say that, but you sort of don't have to.
Okay.
Yeah. It's probably more precise to say that, but it's kind of understood. Okay. Let me ask you a question. What if the domain of F is just a finite set of points? x1 through xn. Okay. Is the function going to be bounded? Sure, right? Because you can take the max value, and that'll be your maximum value, and you take the min of these guys, but there's only finitely many of them, right? So there's no trouble there, right? If it's an infinite set of points, well, then you don't know, right? You don't know. But if it's an infinite set that is closed and bounded, then it turns out to be that the function is bounded. Okay, so there's some sort of like finiteness. There is a sort of finiteness to AB that the open interval AB doesn't have. Right? Okay. There's some sort of quality of finiteness to this interval. Okay. We may not explain what that means, but if you take 131, you'll see what this means in great detail. Okay, so let's do it. We're going to do proof by contradiction. So proof by contradiction. Suppose that F is not bounded. Suppose F is not bounded. Then for all n in the natural numbers. For all n in the natural numbers, right? So for any bar, there's going to be some place where you exceed that bar, right? So for any value, there exists some point in AB where f of xn in absolute value exceeds n. So, right, for whatever n you're given, you know that there's going to be some x of n where you exceed either you're above n or you're below negative n. Okay. Right. Okay. So then you have what do you get then? You have a sequence, right? This thing creates a sequence where the values of your function are increasing, right? Where the absolute values of your function are increasing, right? So then we have some sequence of points, right? So then by Bolzano-Weierstrass. So we have some sequence inside AB. What does Bolzano-Weierstrass give us? You have an infinite sequence inside some bounded set here. You have an infinite bounded sequence. Bolzano-Weierstrass will give you a...
Accumulation.
Well, that's the Bolzano-Weierstrass for sets. Let's use the Bolzano-Weierstrass for sequences. There's going to be a
Subsequence.
convergent subsequence, right? There exists a convergent subsequence x of n is k. Right? Let's say that the limit is c. And that c lies in AB because the sequence lies in AB. It lies in the closed interval AB. We're not going to jump outside of the interval. Yeah.
Could you clarify the picture that you've drawn? I don't understand what we're looking at when we have the...
So, the picture was for this thing here. What we're saying is that our function's not bounded, right? Our function's not bounded, so what that means is that given any bar, that bar is not a bound, right? This number is not a bound for our function. That means that our function must have some point where we jump outside of the bar. Okay, so there must be some, for every m, there's going to be an xm where the value either is lower than negative m or greater than positive m.
Okay.
Okay, right, so the absolute value is going to be bigger than, right, for any n you're given, there's some x of n where our value exceeds that. Okay, right, so the absolute values of the images of these points goes to infinity, right? The limit goes to infinity.
Can you explain that?
Because each of them is bigger than n, right? F of x sub n is bigger than n, right? F sub x, the first guy is bigger than 1 in absolute value. The second guy is bigger than 2 in absolute value. The third guy is bigger than 3, etc., right? So the limit of the absolute values is going to be infinity. Right? The absolute value of the first guy is bigger than 1. The absolute value of the second guy is bigger than 2.
Yeah,
Right?
that makes sense.
Yeah.
I'm a little confused why you couldn't just say, like, why that has to be the definition, and why you couldn't say that there's just some number that it's greater than n. You know, like it's outside of these bounds, and you don't have to say that it's approaching infinity.
Well, you'll see in a second.
Okay.
You'll see in a second, right? One is that we needed to use Bolzano-Weierstrass. Right?
Yeah,
So
I
need
get
a
why we
sequence.
want to set it up that way,
Okay.
but it seems like we're almost, like it doesn't have to be set up that way. And by setting it up that way, we're like limiting our situation. Whatever, sorry.
Okay. I mean, you know, there may be some other way to prove it, but this is how we're going to prove it. Okay. So what's the point, right? We end up with this subsequence, right, that converges to a point in our interval, right? In our interval, right? So here's A, here's B, and there's some point C, and we have this subsequence that converges to C. Okay? But then the limit of f of C, I'm sorry, the limit of f of x sub nk, x of nk, as k goes to infinity, right, in absolute value is infinity, right? But f of the limit of x of nk as k goes to infinity is just f of c, right? Which is not infinity, which is not infinite, right? If f were continuous at c, right, so f cannot be continuous at C, right? Because being continuous at C would mean that the limit of the images should converge to the f of that point, right? But it doesn't. So we have contradiction. The function is continuous on the interval, but there's a point where it's discontinuous. Does that clear things up? Yeah. I mean, you see that, you know, we didn't do anything without reason here.
Yeah.
Yeah. I feel like you still.
No, I think I was a little confused. I wasn't really focusing on the fact that f is not bounded. So by definition, since f is not bounded, there has to be part of it that's greater than n.
Mm-hmm. Yeah.
And I was missing that, and I thought it was
Okay.
just like, we were arbitrarily saying, well, if it's greater than m, we'll say that it's infinitely greater.
No. So we're doing the proof by contradiction,
Yeah.
right? So
Yeah.
keep the strategy. Yeah, Marco.
There's a question. Where did we get the limit of f of x and k as k goes to infinity is equal to infinity? Right before the but, that statement. Well, how do we get that?
That's from here. That's from here, right? Because this sequence goes to infinity.
So every
absolute value.
subsequence also?
Every subsequence. The subsequence is going to go to infinity. Right? Okay. Let's do one more. So, so this is the extreme value theorem, which is one of the crucial, foundation blocks of calculus, even though it's never proven in calculus. So if f is continuous on AB, then f attains a max and a min on AB. Okay. Right. So the picture is you have a continuous function on AB, and there is a point where the maximum value is attained. Right? There's a point where a maximum value is attained, and there's another point where a minimum value is attained. Okay. So there is a definite max and a definite min, and they are attained by your function. Okay. So again, if this is on the open interval, then false. Because you could have f of x equals x on 0, 1. On the open interval 0, 1, you see that there's no place where you attain a maximum value, right? There's no place where you attain a maximum value. No matter what point you choose, on the open interval 0, 1, I can find something bigger and I can find something smaller. I can find a bigger value, right? Like you choose this x, well, I can find some place where the function is bigger and I can find some place where the function is smaller. There is no place where max is attained, no place where min is attained. So this theorem is the hidden heart of calculus. It implies, for example, Rolle's theorem. Rolle's theorem you use to get the mean value theorem. Mean value theorem you can use to get the fundamental theorem of calculus. Mean value theorem you can use to get generalized mean value theorem, which gives you L'Hopital's rule. Right? Everything hinges on this thing called the extreme value theorem, which we never explained. Right. Okay. So I think we have enough. I have 2 proofs. We have at least time for one. So let M denote the supremum of the values. Let M denote the supremum of all the values. We know that it's finite by the previous theorem. Okay. Okay. So that's our M. That's the supremum of all f of x. Okay. Since it's the supremum, then given any number n, we know there must be some f of xn there must be some xn in AB where f of xn lies in m of 1, m minus 1 over n, comma m. Okay, right, this guy is the supremum. This guy is the supremum. So what we're saying is that, look, if I take supremum minus 1 over n, there must be some point down here that lies in this interval here. Because otherwise, we said this many times, right? Otherwise, that's not the supremum, right? Right, okay. So then, now, by Bolzano-Weierstrass again, by Bolzano-Weierstrass, there exists a convergent subsequence, right? There exists a convergent subsequence, x of n sub k, such that x of n sub k converges to some x naught in AB. Right? Let me come back here. Notice that the limit of f of xn as n goes to infinity is m. Right? Because we're taking guys who are in the interval of length 1 over n and we're letting n shrink. Right? So the limit of these outputs is going to be m. Okay, and you can see what's going to happen, right? You say, well, look, by continuity, the limit of f of x sub n sub k, as k goes to infinity, is f of x naught, right? Because the subsequence converges to x naught, the limit of f of that subsequence will be f of the limit, right, by continuity. Right? But the subsequence converges to m, right, because the sequence converges to m. Okay, so what does it tell you? That at that x naught, f attains the maximum value. F attains the supremum, and thus we have a max, not just a supremum. We have an attained supremum, in other words, a max. Okay, and you can see that you can do exactly the same argument to show that f attains its minimum value as well. Next time we'll start off with a different and more amusing proof of this fact. And we'll do some more cool stuff next time. Okay.